Hello everyone. In this session, we will talk about a very important topic, that is eigenvalue problem. Eigenvalue problem is applicable for all types of vibration problem. Maybe it's a single degree, two degree, or multi-degree of freedom or continuous system. Uh, but here we are going to talk eigenvalue problem in the context of a two degree of freedom system. And before we go in the mathematical part of this eigenvalue problem, let's understand some fundamental concept in the case of multi-degree of freedom vibration, whether the two degree of freedom or the multi-degree of freedom, that this eigenvalue problem is a standard form we derive using the governing equation of motion of your system. And eigenvalue problem provides natural frequency of your system as well as the model vector, or we would say mode shape, or the eigenvector. Here in this session, the very first thing which we are going to understand, that what is this mode shape or eigenvector. Because whenever you are having a multi-degree of freedom system, it becomes very important to understand how a multi-degree of freedom system behave at different natural frequencies. So let's start this concept first. When we solve eigenvalue problem, we normally call it eigenvalue analysis. It gives us two things. One is the eigenvalues, another thing is the eigenvector. Eigenvalues simply represent the natural frequency of your system. However, the eigenvector indicates the mode shape. What is this mode shape? Mode shape is nothing but the pattern of vibration corresponding to a given natural frequency. For example, we are talking about a 2 degree of freedom system, and let's say the natural frequency of this 2 degree of freedom system, one is the 8 hertz, another one is 20 hertz. I have taken this data randomly. When the system will vibrate at 8 hertz, please understand, I am talking about the free vibration condition, not the forced vibration condition. The eigenvalue formulation is valid for the free vibration condition. So as I said, that now we are having two natural frequencies, 8 hertz and 20 hertz, that we calculated by solving the eigenvalue problem. Now how we correlate or we physically understand that the behavior or the pattern of vibration corresponding to these two natural frequency, and how we can understand it. Suppose I am having a two mass system connected with the three spring, and this is having two natural frequency, let's 8 hertz and 20 hertz. So what will happen when the system will vibrate at 8 hertz? Now you may think that how the system will vibrate at 8 hertz. So there are two options we can do here. One thing, we can intentionally excite our system, maybe the first mass or the second mass, with 8 hertz excitation. So the system will become a force vibratory system. But please keep it in mind that I just want to explain what will happen when the system will vibrate at 8 hertz. You will find that both the masses will have a particular ratio of displacement. That means if I will define this x2 by x1 corresponding to this first natural frequency, it will be a fixed constant. Particularly in case of 2 degree of freedom system, it will be a positive value. That means it will indicate that both x1 and x2 are moving in the same direction, but the ratio of the displacement of their amplitude will be a fixed value. Similarly, when the system will vibrate with 20 hertz, these two masses again will have a fixed ratio of amplitude, and that would be defined, let's say C1, but it will be a negative quantity. That will indicate that now the system is vibrating and both the masses are moving in opposite direction. But here I am not talking about the phase or the magnitude of amplitude. If you are having a very simple system, for example, all the stiffness are 111, all the masses are 111, that in that case this value maybe you may find +1 and -1. So the +1 will indicate both the masses are moving with equal magnitude in the same direction. The -1 value will indicate both the masses are moving but with the same amplitude but in the opposite direction. So what happened when we solve the eigenvalue problem, we get two natural frequencies as well as the ratio of the amplitude of the two masses. And this is valid for all degree of freedom system, not only for the 2 degree of freedom system. This is also valid for a multi-degree of freedom system. So with this brief explanation, let's again come back to our system. Here I am showing the governing equation of first system as well as the second system. Second system is having damping. First system is an undamped system. This is your governing equation. If you are talking about the free vibration, you will have 0 here. Force vibration, you will have force vector here. Similarly, in case of damped vibration, this is your mass matrix. It will have size 2 cross 2, 2 cross 2. The x dot is actually indicating x1 dot and x2 dot, where x1 and x2 are nothing but the displacement of these two masses. When we convert the system into an eigenvalue problem, we especially consider that there is no force term in your system. So the eigenvalue formulation is primarily done for your free vibration case, and as I said that this is done to get the natural frequency of your system as well as the modal vector or mode shape of your system. And finally we will do it using the MATLAB. So let's understand that how to make this eigenvalue problem. Here I am showing a simple undamped system where M is the mass matrix, K is the stiffness matrix. To get the solution of this second order ordinary differential equation, we consider a standard harmonic solution. We can write it as x1 and x2 will be capital X1 and x2. This is a constant value, and now I am saying that e to the power st, this is my harmonic term. I can also write it x, capital X, and e to the power st. When I will put this solution back to my governing equation, I will derive the characteristic equation of my system, and I can write it as s square m plus k, then having x e to the power st is equal to 0. I can also write it as s square m plus k x is equal to 0. So this is nothing but my characteristic equation, or I can also say that this is my auxiliary equation. And when I will solve this auxiliary equation, it will give me two roots, s1 and s2. By doing little mathematical arrangement, I can convert this this equation. I will make it kx is equal to minus s square m x. Please understand this x is actually representing this vector. K is stiffness matrix, m is mass matrix. Or I can write it as m inverse k x is equal to minus s square x, which can be rearranged as a minus I lambda x is equal to 0, where A is your M inverse K matrix and lambda is minus S square. So this is your standard eigenvalue problem, which is a very powerful mathematical tool, not only important in the vibration, it is also valid for multiple multi-physical field. It is important to solve many physical problems, but here we are primarily focusing in the field of vibration. So this is your eigenvalue statement, and MATLAB has very specific function to solve this eigenvalue problem. In MATLAB we are having a command EIG. If I will solve this command, where A is known as the coefficient matrix of my system and currently it is written as M inverse K, it will give me natural frequency as well as the mode shape of my system. There are different ways to solve this problem in the MATLAB. In MATLAB we can also simply say EIG and K matrix and M matrix. So this is one command where we can simply give K matrix and M matrix. This is another command, but for this first we have to create A, and A is nothing but your M inverse K matrix. So when we want to solve this problem in the MATLAB, what is required? We have to give mass matrix as input, stiffness matrix as input. We can apply this term. So we will get the mode shape and the natural frequency, or first we will calculate the A and then we will supply A. But the MATLAB results are interpreted in a different way. Both the results will not exactly same, but results will be there, but reading the result will be different when we are either you are using this A or you are using K and M. We will see it very soon when we solve the MATLAB. But before that, let's do it for a damped system. And particularly when we are talking about a damped system, the mathematics become little complicated. So far, I have straight away said that it will give you the natural frequency as well as it will give you the mode shape. But when we are having damping term, our eigenvalue results are complex number. So when you will solve the eigenvalue problem for a damped system, your eigenvalues, particularly I am talking about eigenvalue because the eigenvalue problem will give two things. One is eigenvalue, another thing is we call eigenvector. Eigenvalue give the natural frequency and eigenvector gives mode shape. But both are complex. In case of eigenvalue, you got a value alpha plus I beta. In this statement, alpha indicate the decay, and for a normal system, normally alpha is negative value. Beta indicates the harmonic part, so it gives you the frequency. Please understand, when you will solve an eigenvalue problem for a damped system, the output will be a complex number where the real part of the complex number will tell you the decay of the system, and normally it is negative. That means because of the damping, the amplitude of the system will decay with respect to time. The second term is will give you the frequency component of your system. But this is also an important parameter to check the stability of your system, because when you will solve eigenvalue problem for a given system and if the alpha part is positive, it tells you that the system is not stable or it is having some instability, and this is particularly apply when we are solving aeroelastic problem. What problem? I am saying that when you are solving a problem of flutter kind of thing, or you are solving the problem of vibroacoustic, that time this instability also becomes very important. But here this is not our domain. We are not talking about anything about this advanced topic. But you should know, when you are solving an eigenvalue problem for a damped system, it will be a complex number. Similarly, when I want to solve this problem, how I will make our eigenvalue problem. So here you simply remember your coefficient matrix you derived using the state space formulation. What we did when we solved the state space formulation, we considered four parameters x1, x2 and x1 dot and x2 dot. This part we have already covered in our previous lecture. So instead of using two displacement and two velocity, we have defined four state where uh, coefficient, that y1, y2, y3 and y4, and we replaced the entire equation considering this, and there we have derived one coefficient matrix, and I'm writing here this coefficient matrix. This is minus m inverse k and this is minus m inverse c. This is also 2 by 2 matrix, this is also 2 by 2. So overall it is having 4 cross 4 value, and what it is indicating, it is corresponding to this vector which is having y1, y2, y3 and y4 value. And this is what, this is indicating the displacement of the first mass, displacement of the second mass, velocity of the first mass and the velocity of the second mass. So when you will apply the eigenvalue problem, particularly for the damped case, what you need to do, first you have to define this coefficient matrix, and then simply when you will apply this EIG command, you will get two matrix. One will be corresponding to eigenvalue, and when you will see it, you will find that there will be 1 2 3 4, a 4 by 4 matrix. What it will indicate, when you will see this matrix, you will find there will be some complex conjugate value. So actually there will be four value corresponding to this diagonal, but the two value are exactly complex conjugate of each other. For example, if the first value I will write as alpha plus I beta, the second value will be alpha 1 minus I beta 1, then alpha 2 plus I beta, alpha 2 minus I beta 2. So in this way you will find your eigenvalue matrix, where you have to only check this alpha part and the beta part corresponding to one value and the two value, and these values are actually indicating the eigenvalues. If I will simply take the diagonal of this, I will get alpha 1 plus I beta 1, alpha 2 plus I beta 2, sorry, alpha 1 minus I beta 1, alpha 2 plus I beta 2, and alpha 2 minus I beta 2. So now how you will identify your natural frequencies, please understand. Beta 1 and beta 2 are the two natural frequency of it. When you are solving your system in this fashion, the lowest value will corresponding to the first natural frequency and the highest value is corresponding to the second natural frequency. That means MATLAB, particularly when apply the EIG command, the lowest value of the diagonal is corresponding to first natural frequency. So beta 2 is showing you the first natural frequency. Beta 1 is indicating you the second natural frequency. However, if you will see the previous case where you are applying this with just K and M, here the output will what? Here the output will be your omega 1 square and omega 2 square. When you are applying this EIGA, you will get lowest value will be the first and highest value will be the second. Second important thing, when you are making your eigenvalue problem, simply for the K and M value, you are going to give the square of your natural frequency, because you can see here that lambda is corresponding to S square. So whatever you will get here is actually the square of this S value, and S is nothing but the root of your equation that indicates the natural frequency. All these things are actually we study when we do the solution of a vibration problem, and this we have already covered in our previous lecture. So here we will not divert it too much. We just want to explain you that how you can understand the eigen philosophy of the eigenvalue problem, and then we will see the MATLAB part. So these are the two different way. In case of a damped system, your eigenvalue problem will be defined through the coefficient matrix. However, in case of your undamped system, you can directly solve the eigenvalue problem by giving K and M, or you can make another coefficient matrix. This is M inverse K. Here, no need to first convert the system using the state space formulation, but particularly when we are solving the problem for a damped system, you have to first convert the system using the state space formation. There, you will get a coefficient matrix, and solving this coefficient matrix, you will get the eigenvalue. Similarly, when you will see the second matrix up from the EIG command, that is indicating the eigenvector. So, in case of eigenvector, you will again find four columns with four rows. So actually you are looking for the displacement value, because mode shape is what we say. Mode shape is your ratio of amplitude of your system. So you are looking for x2 by x1 corresponding to first natural frequency, as well as x2 by x1 corresponding to second natural frequency. So please remember, when you will go back and check, you have decided that y1, y2, y3 and y4 are corresponding to two displacement and two velocity. So here also first two value indicate the displacement part, and later half is indicating the velocity part. Here also you will find the complex conjugate. So if this is alpha 1 plus I beta 1, it will be alpha 1 minus I beta 1. It will be alpha 2 plus I beta 2. It will be alpha 2 minus I beta 2. Similarly, you will find second value here. So what you need to do here, if you want to pick the mode shape, you have to pick these two values and then these two values, or these two values, or these two. Either of the value you will take. These two are with minus sign, let's say these two will be plus sign, but these are the complex conjugate, so it will not make any difference. Remaining two values are corresponding to velocity. But if you will go and you will run the MATLAB code, you will find the ratio of either these or these will always remain same, but this is valid when you are having your C matrix corresponding to your proportional damping problem. Now again, it is a theoretical part that how you will define the proportional damping. I am not going in that part. This is a separate discussion. I just want to explain you that if you will have a damped system, and how you are deciding your damping is another part. But when you will solve your damped system, you will find the eigenvector in this fashion, and you have to pick top two rows for the displacement part, or last two rows are corresponding to the velocity part. Now if you are taking these two, how you will take this ratio? Because here also you are having alpha and beta, so either you can take alpha 1 alpha 2, you can take beta 1 beta 2, both will give you the same. We'll see it when we'll solve the problem, but I hope that now you are having a basic understanding that how to define an eigenvalue problem and what is the physical significance of an eigenvalue problem. So let's go to the MATLAB window and try to understand that how to solve an eigenvalue problem. So this is your MATLAB window. Here I am not explaining the code line by line because I will explain you here itself. The first two lines are simple. Here I am explaining the what is the k value and what is the m value of my system. This is my mass matrix, this is my stiffness matrix, and you can see here, as I said, that I have two choices. Either I can define a coefficient matrix which will be m inverse k, and then I can get the eigenvalue, or I can directly solve it by giving k and m. So this is first part where we are solving a problem of an undamped system. If I will run my code, I have made a single code, but let's run the code up to only line 15. So this would be the output of line 15. You can see here that V1 is indicating the mode shape. I will just show you that the answer. This V1 is corresponding to the solution of line 14, where I have given K and M as input. You can see here that this is the two negative value. If you will take the you will do the normalization. What does it mean? It means if you will divide this complete column with the first value, the first value will become +1, then something will be here, both will have the same sign. So this will indicate the mode shape. That means when the system will vibrate with the first natural frequency, the ratio of 1 and 2 mass will define by this way. Please remember, mode shape will never give you the absolute displacement value. To get the displacement, we have to solve problem using the response philosophy. What the mode shape will tell you? Mode shape will give you the relative displacement. So in that way, this is also correct. Or if I will normalize it, that will also be correct. In the second column, you can see one value is positive, another value is negative. That means the two masses will not move in the same direction when the system is vibrating with the second natural frequency. So please remember, when you are simply giving k and m, this represent the first mode shape and this represent the second mode shape. Similarly, what is fr1? This is fr1. This is your first natural frequency, this is your second natural frequency, but this is not the natural frequency. It is the square of the natural frequency, and this is in the radians per second. If you want to get it in the hertz, what you need to do, first you have to take under root of this value, then you have to divide it by the 2 pi, then only you will get the final answer in hertz. Let's see the second. This is my v2. V21 means what? The mode shape, same mode shape, but I have solved it by just giving the coefficient matrix. So here you can see the value are different, but if you will take the ratio of this value, you can compare it with the v1, you will find the same value. But please remember, as I said, when you are giving coefficient matrix as input, the second column is representing the first mode and the first column is representing the second mode. Please, I'm going back and I'm explaining you how it will work. When you are solving the eig command using a coefficient matrix, you will get two columns for mode shapes, as well as you will get the diagonal value for the eigenvalue. Here, this is the first value and this is the second value. Similarly, this would be the first mode and this would be the second mode. On the other hand, if you are applying the eig command giving simply k and m, in that case also you will get two matrix. One will be corresponding to eigenvector, another one is corresponding to eigenvalue. But in this case, this would be your first natural frequency and this would be your second natural frequency, or you can say the square of the natural frequency. Here also you will get the square of the natural frequency, but value will be in the opposite fashion. This would be corresponding to first, this would be corresponding to second. Similarly, when you will talk about the mode shape, this will give you the mode shape corresponding to the first natural frequency, then the second natural frequency. So this is your first mode shape, this is your second mode shape. However, when you are solving it giving the coefficient matrix, this would be first, this would be second. So please remember this when you will solve the problem by doing the coefficient matrix. So let's go back again. So here you can see that this is your first mode, the second column, and this is your second mode. And here also you can see both are in the same, both are having the same sign. That means the both the masses are moving in the same direction. But if you'll go here and you will check the magnitude here and the magnitude here are different. Doesn't matter. As I said, mode shapes are nothing but the relative value. If you will take the ratio of 0.5907 and 0.0869, or you will take the ratio of this 4597 and 62880, you will get the exactly same value. That means the mode shapes are relative value. The mode shapes are not the absolute value. If you will see the natural frequency, you can see 3.2 and 6.7, the same value here, 3.2 and 6.7, but this is your first and this is your second. So I hope that now you are clear about how to get the eigenvalue and eigenvectors for an undamped system. So let's move to the damped system. As I said, in case of damped system, what you need to do, first you have to derive the coefficient matrix. Here I am introducing the damping value. This is my damping matrix, and as we have already seen it in our previous lecture that how we define the coefficient matrix. This is my coefficient matrix where these two values are, it is a null matrix of size 2 by 2, it is identity matrix of 2 by 2, then minus m inverse k minus m inverse c. And here I am solving the problem, and you can see here that this is my line 23 response, and you can see here that v3 is representing the mode shape, and you can see here these are not the absolute real value, these are the complex value, and two complex value are exactly complex conjugate to each other. This is 0.003 minus some 0.114i. It is here you are having a plus sign. Similarly, you can see here, and you can see that here also you are having the complex conjugate value. So if someone is interested to find the ratio of the two amplitude, what he can do, he can take these two values 0.103, 0.0141. It will give you the ratio of the displacement corresponding to first mode shape. Please remember, here also we are giving the coefficient matrix as input. So this is corresponding to first mode shape. Here also we are having the same thing, but in complex conjugate form. This is corresponding to second mode shape. Either you will take the ratio of real part or the imaginary part, you will get the same value. In addition to that, this last two row corresponding to the ratio of the velocity of your masses corresponding to a particular mode shape. When the system is vibrating with the first natural frequency, it will have, this is the ratio of the velocity, and you can see that either you are taking the ratio of these two value or these two value, you will get the same. So in case of damped system, you will have displacement as well as the velocity, because first you have converted it using the state space formulation, and then you are solving your problem. When I will go and I will see the frequency part, this is my frequency part, and you can find that this value and this value are the complex conjugate. This is the complex conjugate of this value, and as I said, the real part indicate the decay and the imaginary part indicate the frequency. So the 57.16525 is the first natural frequency. Please remember, when we were solving the problem for undamped system, the output was the square of the natural frequency. But when you are solving a problem of damped system where you have derived the coefficient matrix for the damped system, as we have considered CC in our MATLAB code, it will give you the frequency, but the frequency will be not the square, it will be just a frequency. That means if I am getting an output of 57.16, it is my natural frequency in radians per second. So to get the frequency in hertz, I have to simply divide it by 2 pi. So 57.16, whether I will take from here or here, it will give me the natural frequency, and this is the real part, which is indicating the decay, and it is the effect because of the damping. And you can see here it is negative. Similarly, when you will see the first or the second row diagonal value of the first and second row, you can see here this is corresponding to the second natural frequency. So 82 is the second natural frequency, and to get it in the hertz, I have to simply divide it by 6.28. That means the 2 pi. Here also you can see the real part is negative. So this negative real part indicating that the system is stable. If it would have positive, that means because of the damping, the amplitude of the system will grow, and it is a problem where we are talking the flutter kind of phenomena or the negative damping or self-sustainable vibration. So this is a different topic. There what we do the eigenvalue analysis, and when the system becomes unstable, our eigenvalue solution gives the limit. I hope this explanation will help you to understand the eigenvalue problem, as well as this is our MATLAB code which will tell you that how to get the eigenvalue problem, how to see the eigenvectors, and how to interpret the eigenvalue in eigenvectors, particularly when we are simply giving Km or the coefficient matrix. So with this note, I am closing this session. Thank you.